And so there is no school at all. You go tomorrow morning and you eat a little, bananas and something to get your energy. You go and you do something good for the community, something that's going to benefit our neighbors. You come back and you eat pizza, and then you finish your lab write-up. Yeah, I'm a card. So I did still, move the lab write-up to be due at 7:40 on Friday at the same time as homework 7. So you have those 2 assignments due on Friday. And of course, we'll have lecture on Friday too. Let's not forget that. Okay, I'm going to finish up chapter 3, doing some 2-dimensional kinematic problems and a demonstration. And then we'll start chapter 4 today. So the finishing up in chapter 3 is talking about trajectories. Trajectories are the paths taken by objects that are in free fall. So free fall means that it's flying with nothing affecting it except gravity. So when it's in my hand, it's not free fall, right? When it's sitting on the table, it's not free fall. While it's bouncing, during the time of bouncing, it's not. But while it's in the air, that's free fall. And during free fall, the only thing acting on it is, and I'm going to use the word force here, the force of gravity. Of course, forces come up at the end of today's lecture. But that force of gravity is acting on it throughout the flight. Now, I said, of course, that's the only thing. But I specified previously, as far as general physics is concerned, unless specified otherwise, that's the only thing. What realistically is acting on the ball while it's in flight besides the force of gravity? Air resistance. And then there's a much smaller buoyancy due to the air. So there are a couple other things that are acting on it, but we ignore those unless we're told to include them. So for now, we ignore them. The acceleration is just going to be constant acceleration of gravity acting in what direction? Down. Remember, that constant means that while it's going up, acceleration of gravity is down. While it's coming down, the acceleration of gravity is down. And when it's momentarily stopped, the acceleration is still going to be down, so it falls down. So this picture here is just showing, hey, look, dude kicked the soccer ball. It followed some trajectory, the name for the path, and we can calculate the displacement. Notice that we have our coordinate system specified. When we do these problems, it's important to specify that coordinate system. By convention, we almost always have x horizontal and y vertical for a 2-dimensional problem. But you still need to specify it. You could have chosen to make your system like this. It would just make your problem much harder. Why much harder? Because what direction is the acceleration? The acceleration is down. And so if you chose the xy I showed here, you would have to break that into its components, one component parallel to y, one component parallel to x, and you'd have acceleration in both the x and y directions. Well, that makes life harder. We don't aim to make life harder, we aim to make life easier. I know you're all doing your physics problems and you're like, easier my tail, this is hard. But we could make it much harder. We don't want to. We want to make it as easy as possible. So that's the reason for using vertical and horizontal, so the acceleration is all in one component direction. Now later on, we'll have situations where we will rotate the coordinate system, but once again, we'll rotate it to make it easier. Since we have our coordinate system, so the acceleration is only in one component direction, during the flight of my projectile, in the direction that has 0 acceleration, what would you tell me about its velocity? So the component of its velocity parallel to the 0 acceleration, in other words, horizontal. It's going to be constant. So the whole goal of this big, complicated figure is that you see the blue circles for each, or the blue arrows that I'm circling. My brain works really well some days. They're all the same length. You can't see, I didn't circle one because the magenta was on top of the blue. But the horizontal velocity stayed constant throughout the flight. So the picture down below, they broke them out and you see, look, those were constant. Just like we had on that pretest, you could take the horizontal motion and plot it out, and you see that the space between each one is the same distance for the same gap in time. Now in the vertical direction, you see that the vertical components, the orange, got smaller as it went up. Velocity was up, but acceleration was down, so the speed slowed down because they're opposite directions. As it came down, it got faster. Velocity was down, acceleration was down, so it sped up in the direction of motion. And so the spacing, you can see these spacings get bigger and bigger. This space here is bigger than this space here by a reasonable amount. It's not super large, it's longer time frame, you would have seen bigger difference. But the spacing is changing because of the changing speed. So how do we work a problem? Let's start right now working problems. So here's a trajectory for a fireworks explosion. I love fireworks. And so we have a little ball that's fired with some unknown speed v-naught at an angle of 75 degrees, and it's going to end up at a height of 233 meters and a horizontal displacement of 125 meters. What we do to solve problems like this is we solve two separate problems. One problem, the horizontal direction, the x component. The other problem, the vertical direction, the y component. So I break my variables up and I say, okay, x initial was equal to 0 x final is equal to 125 meters. Vx initial is equal to, I know the angle, but I don't know the magnitude. And that, I need to get just the x part. So how can I take that unknown v-naught, or v-naught, and find just the x component of it? What's my method going to start with? There are at least people talking to their neighbors, which is a good thing in this case. So we have, here's my initial velocity v0, and we know that it is at an angle of 75 degrees above the horizontal. So I'm going to make a right triangle with the two component directions. So since this first dashed line was the x direction, from the bottom I made a dashed line parallel to the x component, or x direction. From the tip I'll make a vertical line, one that's parallel to the y component. And I'm trying to make this straight. Obviously I failed a little there, but... Okay, so pretend that's a straight vertical line. So I have a right angle right here because my components have to be 90-degree angles. And so now I have an angle. I have the long side, the hypotenuse. Here's my Vx0. Here's my Vy0. Which side of the triangle is Vx0? Adjacent. And so the trigonometric function that relates adjacent and hypotenuse is cosine theta. Cosine theta is adjacent over hypotenuse. So that means solving that for V0, Vx0 is going to be V0 cosine of theta. Ax, what is Ax equal to? The horizontal acceleration. It's an answer we all should have. What's the acceleration that's acting on this ball? Okay, I put minus there. It's kind of redundant to have the arrow down and a minus sign, but I do it. So in the horizontal direction, how much is that? 0. So I have my initial and final positions, the initial velocity, but I don't know V0. That's what I'm going to be looking for. And I have the acceleration. There's only one other kinematic variable we use. What's that? The time is the one other variable we use. So I don't know the time. Do I care about the time here? No. But time is what connects the two separate problems. Because the time when it reaches its final x position is also going to be the time when it reaches its final y position. So time is what connects them. So I don't know the time, and I actually don't care. But I'm still going to be using time so that I can connect the two equations. I will solve one side for time and then put that in the other. So let's just take this right now. What kinematic equation would combine all these variables? There's lots of ways you can say it. One long way of saying the whole equation, but there's lots of short ways, like the one we use 90% of the time. So I have that equation. Now, acceleration in the x direction is 0. I always put my zeros in immediately. So that's a 0. My x initial was 0. And so I'm left with a pretty simple equation. One that says, for Vx0, I will substitute V naught cosine theta multiplied by time. So if I solve that for time, so there's an equation for time. I don't know the answer because V0 is unknown, but it's an equation that relates time and V0. Now I will go to the y direction. So I have to do the same type of work, but now for the y component. What was it? 133, 233. So looking at my picture, Vy0 is the opposite side from the angle given. And so sine theta will relate opposite hypotenuse. So Vy0 is V naught sine theta. Ay is minus g because we have the acceleration of gravity acting downward. That's where the minus sign comes from. And so just like before, I have this equation. And again, I'll put in my zeros immediately. The y initial was the only 0. And then I will substitute t in. So I will have an equation that has for the only unknown speed. And so my equation will now be, excellent work, so that parenthesis is the time. And notice I substituted for Vy initial and for Ay. And so there I have an equation that I can solve for V0. Now, we're pretty smart people here, right? Everyone of you is smart, right? Yep. So, well, no, I do believe that. So we can cancel the V0s. We can combine sine over cosine. What's sine over cosine? Tan. So I have, I'm going to move this to the other side. What am I solving for? The V initial. So I need to do a little rearrangement. Now, of course, I worked this out yesterday. I don't remember having this equation, but I mean, shouldn't have made a mistake. Shouldn't being an operative word. And so we calculate V initial equals plus or minus. Well, I'm just looking for the speed. So I'm not going to take the minus answer. I'm only going to take the plus answer. Square root of my X final was 125. $65, right? 75. So you have to put that in the old calculator. And I really do worry I made a mistake. Why? 125 times tangent of 75 degrees. Is that going to be?
What happened to the t squared on the x? Like, if you go that out.
Here, it was 0 times t squared because the acceleration was 0 there. Going to have to trust that tangent of 75 degrees is bigger than 2. Tangent of 45 is 1. What'd you get?
69.96.
Okay, now we have an answer. Somehow I don't feel really confident about it. Alex?
I got the same answer solving it a different way.
Okay, Alex got the same answer solving a different way. That makes me feel more confident because one way you can do it is to solve it a different way. What was your method, Alex?
I knew that since the sine of the theta times the initial velocity would be the y velocity initial.
Mm-hmm.
So I took the equation v squared equals v initial squared plus 2ad from the kinematic equation.
Okay.
And so I just I figured out the v initial squared because v squared final will be 0 because that's peak. And then so I solved for the v initial and then solved for the total initial velocity.
Okay, now I have to admit, and this is always a little embarrassing, that's a better way of solving this specific problem. It's a better way because it was much simpler, right? The way I did it is the way you are going to end up solving many of your problems, but he used the fact that he knows the vertical component is 0 at its highest point. And so under the assumption that it is, did it say that it was at its highest point? Assuming that it says, yeah, it says at the highest point. As long as that was the highest point, then he knows that final speed is 0, and that method is a quicker way to get there. Let's say you do this on the test. If you do it a right way, it'll be fine, right? We're not looking for doing it the fastest way, the teacher's way, just doing it a right way. So let's say that we didn't have Alex to give us a confirmation by doing it a different, simpler way. How can I check to make sure this is the right answer? Yeah, plug it back in. So I can take this and say, okay, just looking at this simple equation, x final is v0 cosine theta. Well, I didn't calculate t now, did I? Can't put it back in that way because I have to go ahead and calculate t. So, what was that?
Plug it in your t.
Well, yes, but that would be circular. But I could plug it into my t equation, then plug my t equation in over here and see if I get the right y. That would be a way of checking. So you can plug the numbers back in to check. Or you can solve it a different way. If you solve it 2 ways and you get the same answer, it's a pretty good sign. Okay, so that's one example. Here's another example. You have a rock that is fired out of a volcano. We've got lots of things going on Earth right now. We've got fires burning up California, Oregon, Montana. We've got flooding in Florida. Puerto Rico's getting destroyed right now as we're in class. We've got North Korea to worry about. But we don't have volcanoes to worry about at this very instant, as far as I know. But if there is a volcano, one of the things you do have to worry about is, hey, stuff shoots out. We call it ejecta. And so here we have a piece of ejecta. If you're close enough for that thing to hit you, it's bad times, right? So the problem gives us now the initial velocity. You know, it has both the speed and the angle. And it tells us that it's going to land at some location 20 meters below the horizon and asks you, what is the angle going to be? How can we go about solving this? I'm not actually going to solve it because I think I'm going to run out of time if I do. How would you go about solving this?
Find the x and y velocity.
Okay, find v x initial equals v initial cosine of theta initial. Vy initial is equal to v initial sine of theta initial. That is definitely a first step to take. Then what do you do with that? Remember, we break it into two different problems, the horizontal problem and the vertical problem. And now in this vertical problem, we know, let's say y initial is equal to 0, so y final is equal to minus 20 meters. We know those two numbers. Now going with the equation that Alex used, for the vertical direction, we know the acceleration, g pointing down. We know the initial velocity. We know the change, the initial and final heights. The only thing we don't know from the equation Alex used is the final velocity. So I can use that equation, find the final velocity. How many answers do I get when I find the final velocity? 2. Because when you do the square root, you get a plus or a minus. But looking at the situation, which answer is correct? The negative. Okay, I will do that. Well, I'll do it here. It's short. So v final squared, vy final squared, minus vy initial squared is equal to 2ay, y final minus y initial. So vy final equals plus or minus. We know we're going to go with the minus. Square root of vy initial squared plus 2ay, y final minus y initial. And we have that plus 2 times minus 9.80 meters per second squared times minus 20 meters minus 0. And so you put that in your calculator and it gives you the final y velocity. Did you calculate it, Alex? I saw you working in your books. I thought maybe anybody got that number? You said 24? I'm just trusting you now. 24.75? What? 45. Okay, so I'm trusting Gila here. So we have the final speed in the y direction. What's the final speed in the x direction? Acceleration is 0, so it's going to stay v0 cosine theta. So what do we get when we put that in the calculator?
Actually got for the last one, negative 14.2.
Uh-oh. I'm going to go with the newer light. 14 point what?
I got what you got.
0.2?
2-0.
20. Okay. You said that's what you got too?
No, I got what you got.
Oh, you got what Gila got? Uh-oh. You're,
How about it?
24.95? Okay, so we have 3 people who got 24.95. Let's assume they're correct. What do we get for 25 times cosine of 35? 20.48? So now we have the final velocity has 2 components, 24.95 and 20.48. How do I find the angle? Moving that to the side that has the angle so it's not confusing. So tangent relates opposite and adjacent. And so I would have yay. I've got to get a new pen, I think. This is silly. Tangent of theta is equal to the opposite side, 24.95. Uh-oh, there we go. Over the adjacent side, and then we can find theta. So this angle may or may not be right, but 3 out of 4 people will think it's right. Based on the calculations, 3 out of 4 people came up with that number. And so theta is just arctangent of those numbers. Now, a few things to point out. My y final velocity was negative. Why didn't I put negative in my arguments for tangent theta? Why didn't I put tangent theta is equal to minus 24.95 over 20.48? Okay, good thing I asked the question. The reason is, in my triangle, the length of the side was positive, right? The vector is negative, but the length of the side is a positive length. So given my triangle, that was a positive number. So you have to, right, you can't just throw numbers in the calculator without thinking about them. You have to pay attention to what they mean and why you're doing your steps. Now, some things to make life a little less mysterious. When you throw that ball up, we know that its speed slows down as it goes up, speeds up as it comes back down. You have the same acceleration in the vertical direction the entire time. Because of that same vertical acceleration, it turns out you're going to have the same speed at every height, right? So if you're 1 meter off the ground, whether you're going up or coming down, it's going to be the same speed. When you go I said 1 meter, I put it up here. That's about 2 meters off the ground. You're at 1 meter off the ground, it'll be a different speed than at 2 meters, but it'll be the same whether it's going up or down. That's why when we did our equation, the v final squared minus v initial squared is equal to 2ay times y final minus y initial. We had 2 answers, plus or minus. The plus answer would be if it was going up and at that elevation. The minus answer is if it's going down at that same elevation. Eric, what was your comment?
For the, where did we get the x component of the
Velocity?
vector, final vector? X
Because the acceleration, that's a vertical line, believe it or not. The acceleration was all vertical. So the acceleration in the x direction equals 0, which means the velocity is not changing in the x direction. So we found the initial velocity, and that has to be the final velocity for the horizontal direction. Sorry, I glossed over that. Okay, some simulation. Unfortunately, I don't have Microsoft Office on this. And so I have to shift to a different computer screen, one I can't draw on, and one that I can't record from. so that you can see this. Probably it just interrupted my recording. We'll see at the end of the class. So this here is a simulation of a trajectory. So I have a bike, motorcycle, and he's trying to jump. He's Evel Knievel. When I was a child, Evel Knievel was the bomb, okay? You guys don't even know who he is probably. I'm claims to fame like, broken every bone in my body. Huzzah! Gonna jump the Snake River Canyon. Kind of. Almost made it. So we have a motorcyclist who's trying to make this jump. And so what we need to do is try to find what angle and speed will get him to the jump. Now, if we know the distance, we can go ahead and solve the problem just like I did earlier using the same methods, but we're going to do it just by feel. So first, let's see what happens with these present numbers. So he overshot, going at a speed of 8 meters per second, an angle of 45 degrees. What can we do to shorten the distance? Okay, Gila was closest. What did you say? Change the angle. Was it you, Edward? No. Irving? Okay, Irving said increase the angle. Okay, so I'm going to go with Irving. I'm going to increase the angle, which is one of the two options that Gila had. So I'm going to increase that angle from 45 degrees to, let's say, 50.7 degrees. Try it again. Still overshot, so let's just go to a bigger angle. 58.5 degrees. Oh, yeah. Hit the sweet spot. Now, what if we had done the other way? Gila just said change the angle. What if we had gone to a smaller angle? What happened then? Only Irving answered. Anyone else? Well, I changed it to 30 degrees instead of 45 degrees. It's what?
It should at least be closer.
Okay, so I chose it symmetrical once we found there was, yeah. So we hit it again. Now let's go back to 45 degrees. Oh, wait. I thought there was a reset the whole thing. There's not. Okay, 45 degrees. There's another option. What's the other option for changing the distance? Okay, slow them down. So we will slow them down. Just barely, man. Slow them down a little too much, right? Because you don't want to be that close when you're doing the jump. You want to be in the middle. Okay, so there at 45 degrees, we're able to do it 7.4. Now, some simple things. As you change the speed, of course, you go farther, right? But I can make it a very flat angle and shorten up the distance. Clearly, that wasn't enough. Within our guidelines, 10 meters per second, I can't do it with 20-degree angle. 60 degree, yep, still too far. So I can't go at 10, but if I slow it down to 9, I should be able to land on there. Nope. Okay, we were at 8, so. At 8.4, you're just at the end, so. Now, if I have it steeper, what's that doing to my initial velocity? My speed stays the same, but if I go steeper, what does that do to the initial velocity? It doesn't increase the velocity because the speed's the same. It lowers the x component while at the same time raising the y component. So if you go up faster, that's going to make you stay in the air longer. Because, your speed, the speed when you land the vertical direction is going to be the same as the speed you started if you land at the same height. And since change in speed is a delta t, if you have a bigger change in speed, you're going to have to be in the air longer. So you're going to be in the air longer, but you're going slower horizontally. Whereas if you go to a flatter angle, you're in the air less time, but you have a faster horizontal speed. We use the same thing when we're playing baseball. If you're the outfielder and you're trying to catch that runner who's going from third to home, You want to get it to home. You want to get there fast or slow? Fast. So you have to gauge, and every baseball player is thinking this without knowing there's any physics involved. You have to gauge your throw, so you're throwing as hard as you can at the flattest angle you can and still get it to the catcher. And of course, if you know too much about baseball, you know that they actually aim to bounce the ball somewhere around pitcher's mound, so it bounces into the catcher, making it easier for the catcher to handle and making it so you're throwing on a flatter trajectory, which actually gets there quicker. So baseball players are using this physics information, but they're not doing calculations. They're not sitting in physics class now saying, I got this speed, if I throw this angle, yeah, you never get it done. But they have essentially built up tables of physics calculations in their head that they don't even think about that tell them what angle to throw it at. So if I want to throw the ball to, Brady says no. Gila's using her, okay, I won't throw the ball. Okay, Gila, so if I want to throw it to Gila, I have options. I can throw it up, and it comes down and comes to her. Yay. I don't always hit the students. And I don't always catch the ball either. I could have thrown it at a lower angle, but I would have had to throw it faster, which gives her less time to respond and makes it more of a problem with her potentially not catching it. I once did this to a student, and I threw a nice lob like I did to Gila, and she's like, ah! You're supposed to respond in some fashion. Okay, so I don't know. That to me, that's kind of fun, just seeing in action how this works. Please be 3. I think it's 3. No, it must be 2. I'm back. There we go. Okay, so now we're back to this. There is, in your textbook, I think, a range equation. An equation that won't be on your test. The reason is that range equation is specific only to if it leaves the ground, or it starts and ends at the same elevation. In real life, that's not really realistic. But if it starts and ends at the same elevation, then you have a simple equation that you can plug in without going through all of the work. On the test, you won't have that equation. I will want to see you go through the work to find if it starts with this angle and this speed, starts at this height, ends at this height, how far to go. I'm going to want you to show breaking it into your y components and your x components. Generally, you solve the y components to find the time because it's a simple problem. Yeah, it's quadratic, but it's simple. And then you take that time, put it into the x components to find the distance. If you want to see the calculations on there in the homework, homework help section, I did one on projectile motion. It's not actually the same one as I did with, was it Rebecca? Wasn't you that came in? Yeah. I rewrote it and did all of the work to show how you do one of those problems, breaking it into the components, finding the time, plugging the time in. And I came up with the true range equation here, which is a pretty large and ugly equation. That one you could use all the time, but you're not going to get that either because what I want to see is that you know how to do this work here. And then the one that's in the textbook is for the special case where the difference in elevation, the height is 0. And if that h is 0, then it just simplifies to the equation that's in red. So you can look through and see the actual application and work there. But right now, we have more fun things that we have to do. And the first of those fun things we have to do is the demonstration for today. Now, this is a very famous problem in physics. It's called the monkey gun problem, except for we don't use the terms monkey gun anymore because people say, ooh, that's cruel and inhumane. But nonetheless, I will portray it with the original story. So a game hunter goes hunting for this rare monkey that is a nervous monkey. And when you fire the gun, it hears the bang, and it always drops like a possum, right? It just has that physiological response that makes it lose consciousness. It falls when you fire the gun. And so when you're aiming at it, you have to take into account that it's going to fall. So the question is, where do you aim if you know that that monkey is going to fall the instant you shoot your gun? Do you aim so that your gun is pointing at the monkey, somewhere below the monkey, like where it's going to be when the bullet gets, at the time the bullet gets over there? How do you aim? Okay, Alex?
Straight at the monkey.
Alex says straight at the monkey. Why would you aim straight at the monkey? He's right, okay. Why would you aim straight at the monkey?
Because your bullet and the monkey have the same acceleration you have.
Your bullet and the monkey have the same acceleration, so they're both going to deviate from the place you aimed or where the monkey was by the same amount in the same amount of time. Right? Your bullet's trajectory, instead of going straight line like this, is going to curve over, and the amount of drop from that straight line is going to be exactly the same equation as the drop for the monkey. So I need somebody to come and help me with the demonstration. Number one is you're going to check to make sure I'm not cheating, and then verify for the class what happened. And we have to keep in mind that I'm not the world's greatest aimer. If I was a good cheater, I would have a little laser pointer that I just stick in there and look at where the laser pointer was. So who wants to come and make sure that I'm verifying this is a good experiment? It's really easy. Okay, Gila. So Gila, come on up. Now, first thing is, here's the target. I put circles around the 3 from practice shots. So verify there's 3. They're all circles, so we won't have any fakery. Now I'm going to put this up there, and your job is basically going to be to, like, stand over here, to make sure if it hits, and then we'll check and see where it hit. And of course, if it doesn't hit, that means either my physics is bad or my aim is bad. I just hope it hits because, well, as you probably can, I know my physics is good. It's the aim that I'm not so sure. So I have to check the aim, especially because after I finish practicing, I tried to adjust it, but didn't have anything to aim for. And I'm definitely aiming too high right now. Okay, so I think that should be good. I have a ball in here. Ram it down there to arm my gun. Double check that I didn't change it while I did that, which I changed it dramatically while I did that. Okay, so now I think we're good to go. I turn this on. When the ball comes out, it's going to go through this little photo gate. When it goes to the photo gate, that's going to trigger the switch that drops the target. So you ready to do that? All right. Pray that it works. It's also hard to. Did it hit?
Oh, yeah.
Where did it hit? You have to flip it open to see.
Oh.
Okay.
Right there.
So there it is. Now, it wasn't on the bullseye. It was out here. But we hit the target. Hooray! If that was the monkey would be stunned because I would, use stun bullets. Okay, truth is, I'm a very pacifist person. I would never go hunting, but it's a physics example. It's an example to show that, yes, I had to aim straight at the target, and then the ball fell the same amount the target did while they were flying through the air. Now real life. Real life raises its ugly head. In real life, we have air. And air makes a difference. So let's say you're a baseball player. You're taking a nice swing at the ball. You want to hit it out of the park, right? That's everybody wants it. They want to hit, as the commercial way, chicks dig the long ball. So you want to hit a long ball, but the air makes a difference. And so this graphic, which comes from this website, shows the difference in what would happen if you were in vacuum. This red line is the general physics answer for how far you're going to hit the baseball. The blue line is what really happens because there's air in the stadium. And so the ball, the initial separation here is because of spin. The ball goes up and it comes down and it lands a fair amount shorter. Now, with that in mind, why do people like to go to Colorado to play baseball? There's less air. You're closer to that vacuum trajectory. You get a little more distance for the same hit on the ball. And there's a lot of really good information if you're interested in baseball and how what we're learning here applies to baseball at that website. Okay, the first of our clicker questions, which, give me a second. I'm sure there's a way. I'm just going to go here and restart it there. Because of the animation in the PowerPoint presentation, it wasn't working. So yeah, you can answer now. So far, Gila, Ashley, and Jamie have answered, just so you know if you tried to answer early. What variable ties the vertical and horizontal motion of a trajectory together? And lest people forget, so we have people who haven't answered yet. Alex, Corso, well, they both answered. Eric, Augusta, Brittany. Got Augusta, just Eric and Brittany now.
Channel 33.
Channel 33. You getting logged in, Brittany?
Mm-hmm. Sorry, I'm just reading.
Okay, you're in, Eric, multiple times now. It changes the color when you answer again, so like Rebecca just hit it third time. In case you wanted to know. Okay, Brittany's in. Everybody's answered. I want people to get their points. That's why I sit there and wait and call names and stuff. So one person said acceleration, 9 said velocity, and 18 said time. So let's go straight to Ashley Morrow. Give us your answer and why.
Well, when we talked about like the x-axis and the y-axis,
Mhm.
we can care about the time in the last problem that we worked out, but that was how we could connect the distance from it going up and the distance that it fell down.
Well, not up versus down, but up versus horizontal. Okay, so the answer was time, D. Okay, and that's right. Now velocity, the velocity has components in the x and y, so I can see why a lot of people answered that. But in your solution, it's usually time is the variable that ties the horizontal and vertical motions together. Now to forces. Obviously, with 1 minute left, we're going to have a very minimal discussion of forces here today. But a force is anything that pushes or pulls. So if I come over here and I push on Churaka, I have applied a force to her. And so if we go back historically, people like Aristotle thought that objects just had a natural position. They naturally want to fall to the ground. That was a natural position. And that you had to put violent action, i.e. a force, on the object to make it do something else. So basically, he would say that if I take this little weight box, it wants to be at rest here. I push it, that's a force. I stop pushing, it comes to rest. First Galileo and then codified by Newton came up with a different idea about why things move. And so the next section, chapter 4, we're going to be talking about forces, things that push and pull and how they affect motion. This is what we call dynamics. What we've been studying was kinematics, how things move. Now we're going to dynamics, which is why things move. All right.